All right, so yesterday we ended off here talking about the average rate of a reaction and looking at over time. And so an average rate, remember, an average rate is just over a certain time interval. You're going to do final minus initial over whatever time interval we're looking at. And so in here, the thing we finished off on talking about was that the average rate of the reaction is going to slow down over time. And so what we see here, we see that as this reaction at time 0, when it first starts, 1.9, and as it goes on, it gets slower and slower and slower. And so we know, we talked about chemical reaction, the rate will slow down over time because you're losing reactant molecules. And as you have less and less molecules, you have less molecules that can collide together, and that results in a slower reaction. And so that was the average rate. And so we can look at now what we call the instantaneous rate. So what we can do, if you're familiar with calculus, this will should make a lot of sense, but even if you're not, it's okay. What we're looking at here is the instantaneous rate. And so the instantaneous rate would just be the rate at a specific instant in time. So we're not looking over a certain time interval, we're looking at a specific time. So here on the graph you see time equals 0, or you could see at time equals 600. So here we're not going over a certain range. And so if you have a graph of concentration versus time, and you want to know the instantaneous rate or the rate at a specific moment, all you have to do is find the slope of the tangent line at that point. And so hopefully we remember that slope is rise over run, or you could do change in y over change in x, right? So what all you would have to do, and so remember a tangent line is a line that only crosses that point at one time. So here, this point right here, it only crosses it once, and you could extrapolate out and you could find where it crosses over different axes, and then you could find an x and y coordinate for two points, and then from there you could find the slope. Same thing here, right? If we want to find the instantaneous rate, right, at time equals 0, we just find the slope of the tangent line at time equals 0, and then from there we could find that once we find that slope, we would then know that is the instantaneous rate. So make sure you're able to distinguish between finding the average rate, which is just what we looked at here, final minus initial, right? We're dividing those, or doing instantaneous rate, which is just the slope of the tangent line. So more often than not, you'd be given this graph. You have a piece of paper, right? You can use your piece of paper to draw your best tangent line and then do your best to find the curve. Understand here when we're doing instantaneous rate, we may get slightly different answers depending upon our tangent line, but they should still be close. And so what we see here, remembering that all reactions slow down over time, you can see the slope of this line right here is really steep, which would be a really fast rate. And you can see if you were to look at the tangent line going through here, when we get down here, this slope is not as steep. And so what that means is the rate is not as fast. And so what we can see here is eventually if we were to take this graph out, you would eventually reach a point where the slope would be 0 or the rate would be 0, and that means the reaction has stopped. So we know the best indicator of a rate of a reaction is the instantaneous rate near the beginning, because that's the fastest the reaction will ever occur. So this initial instantaneous rate is the fastest the reaction will ever occur. And so that is in the initial rate, or this initial instantaneous rate is of value to us, is most important to us, because we know that this is the fastest the reaction will ever occur. And then from there, it's going to slow down. And you can see that here with the different slopes. The slope is getting closer and closer to 0 as we go on. And so when we look at reaction rates in stoichiometry, and so looking at our balanced chemical reaction that we're dealing with, we have to account for the coefficients. Now, luckily for here, it's 1 to 1 to 1 to 1. So right, we have a 1 to 1 ratio of this reactant to this product. And so when we write the rate, we can write the rate equation in one of two ways. And what you see here, when we're measuring this, we could account for how fast is the reactant going away. That's why you see it's negative. Or you could write the rate in terms of how fast am I making a product. So we're gaining the product, and that's why you see it's not a negative. It'd be a positive value here. And remember, delta is change. So final minus initial. So final concentration minus initial concentration divided by final time minus initial time. And so we can look at the rate. You can look at it either with respect to the reactants, or you can look at it with respect to the products. Either one. And so what if it's not a 1-to-1 ratio? Not all of our chemical reactions are going to be 1-to-1. Here we see it's 2-to-1. 2-to-1. So what would we do in the case where it's not 1-to-1? So we would look at writing it. So all you do is you could put a fraction in front. The denominator of that fraction is the coefficient. And so what we see here and what this is telling us, so notice, first thing to notice here, this is negative 1/2. So negative because HI is a reactant. Remember, brackets just mean concentration, molarity. Delta's change, so changing concentration over time. We're losing the reactant, that's why it's negative. And then the half. So what we have to look at here is they're comparing it to your product. For every 2 of these that we lose, we only make 1 of these. So we are losing these at 2 times the rate that we're gaining our product. But if we want to make these equal, that's why you see that they've multiplied it by 1/2, because 2 times 1/2 would just be 1. So we can see here that all we're doing is taking this coefficient and we're putting it as the denominator of a fraction. And so the coefficient here is a 1. 1 over 1 is 1. That's why you don't see it there. And so we can relate, again, the rate we can write in terms of our reactant, or we can write it in terms of our product. Again, understanding that I'm losing the 2 of these for every 1 of these that I'm making. So I have to slow, quote unquote, slow that rate down by multiplying it by 1/2 to make them equal to each other. And so when we look at a generic equation, little a's representing your coefficient, big A's representing the chemical or the molecule that we're talking about. And you can see that negative for A and B because they're reactants. You got the change in concentration of A over change in time, change in concentration of B over change in time, and then 1 over A or 1 over B, whatever that coefficient is, whether it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever it might be. Going over here, notice they're positive values because C and D are products. Again, change in concentration over change in time. Then the coefficient we put on the bottom here. And so again, this is just a way that we can relate the rate of a reactant to the rate of a product. And the one that we would choose in a problem is one that we could measure a change in concentration of. And we can't measure the change in concentration of everything. It's hard to measure the change in concentration of things. So one thing that we'll look at later in this unit is when we have a chemical that changes color. So if you have a chemical that's a dark purple color, and you see as that dark purple color goes lighter and lighter and lighter and eventually it gets clear, we know that we started with a certain amount of our dark purple substance, and then once the solution is clear, we have none of it left. And so we can measure the change in concentration of that. There's a method that we use, a formula that we can use, and so we'll talk about that later. So what A or B or C or D, what we pick is all going to depend on what's the easiest thing that we can measure a change in concentration of. And so we can gain information about the rate of a reaction by seeing how the rate changes as we change concentration. Go back to the very first thing that we talked about, right? The first things we talked about was how can I change the rate of a reaction? How can I speed it up? How can I slow it down? And the way we can speed up a chemical reaction is by changing the concentration, or the way we can slow down a chemical reaction is changing it by decreasing the concentration, right? If you decrease the concentration, you have fewer particles, which means there's less collisions, which means it moves slower. Increasing the concentration would give you more particles, which would give you more collisions, which would make it faster. And so what we can do is we can conduct the same experiment multiple times So we can do trial 1, trial 2, trial 3, trial 4, trial 5, whatever. And from that, we can vary the concentration of one of our reactants, right? We don't want to change the concentration of both reactants because if you change two variables at one time, you can't tell which one is affecting the rate. So what you'll see in our data table is we'll change one concentration, leave the other one the same, and we'll see if the rate changes. And if the rate does change, then there's valuable information that we can glean from that. And so we can look at an experiment here. So 6 different trials. This is the net ionic equation of the reaction that they're performing. You start with a certain amount of NH4 and a certain amount of NO2. And you notice the concentration. So here in the first 3, we left NO2 minus the same. And we just changed NH4 plus. And you can see from here to here they doubled it and they doubled it again. Well, what can you see here? We can see that the rate doubled and the rate doubled again. So we can tell that there is a relationship between the concentration of NH4 plus and the rate of the reaction. So we know NH4 plus plays a role in the rate. And then when you look at experiments 4 through 6, you can see that NH4 plus stayed the same, NO2 minus was doubled, and when NO2 minus was doubled, we see the rate was also doubled as well. So we know NO2 minus has an effect on the rate. But notice we didn't change both at the same time. And so here you can see that when NH4 doubles, the initial rate doubles. Likewise, you can look at 5 and 6, and we can see that when NO2 doubles, the initial rate will double as well, right? So there's a direct relationship there between the change that we're seeing when we change the concentration and what we observe with the rate. And so what we know, and remember this sign just means proportional to, we know, again, this chapter that we're dealing with is chemical kinetics. Chemical kinetics is dealing with how fast the reaction occurs or what is the rate. And so this symbol here just means proportional to. So we know that the rate is proportional to NH4 plus. We know that the rate is also proportional to NO2 minus. So we can write an equation here, and this says the rate is proportional to the concentration of NH4 plus times the concentration of NO2 plus. We can go back here. If you double this concentration, the rate would double. If you double this concentration, the rate would double. So if we doubled both concentrations, the rate wouldn't double. You would think the rate would quadruple. And that's kind of what we're saying here when we multiply the change. So if you double this and double this, 2 times 2 is 4, so the rate would be 4 times greater. And so when we look here, remember we're talking about how do I make an equal sign? We use a constant. And so the constant that we're going to use is a lowercase k. We call that our rate constant. And so the important thing here is to understand that this is called a rate law. The rate law is going to tell us very valuable information about chemical reactions. You're going to learn later this week how to write rate laws. The main thing to understand here, what are the different components of a rate law? Well, you have a rate, and the rate is going to be equal to k, and that k is going to be a constant. It's called the rate constant. So rate equals k, and then we're going to multiply that by the concentration of our reactants. And you don't see it here because the exponent is 1, but we're going to raise the exponent. We're going to have an exponent here. And I'll talk more about that exponent here in the next few slides. But here it's going to be a 1 and a 1, and we'll talk more about that. So it's just rate equals k times the concentration of your reactants raised to some power. In this case, the power is 1. And so rate law shows the relationship between the reaction rate and the concentration. So again, if it doubles or quadruples or whatever, how does that affect the rate? And what is the exponent? So the exponent will tell you the order of the reaction with respect to each reactant. So since this is the rate law that we got, the reaction is first order with respect to NH4 and first order with respect to NO2 minus. Again, the exponent is 1. Tomorrow, we're going to dive more into this, and we're going to look at why is the exponent 1. So don't stress about why the exponent is 1. Understand that the order, because the exponent is 1, it's first order. Later this week, you're going to learn different things that are true about first order reactions. Don't worry right now about, well, what does it mean that it's first order? We'll talk about that later. All you need to understand is the generic format that we have here of our rate law.